Good morning, everybody. So let's start, guys. It's a pleasure this morning. We have Siav. Siav is a company working on document management systems and archival systems. And today they are presenting us their research and development branch and what they are doing for search. In particular, we're using a hybrid solution between traditional models and neural models. It's really a pleasure to have this talk today, and that they have been able to come physically here in our classroom and with a so big staff. So maybe it's easier if you introduce yourself and present your company. Thank you very much.
To all the students, we are a software house based in Padua, but we have branches all over Italy. And our core business is document management and digital processes management. But before we get started, we invite all the students also to get in touch with us. Nicola Ferro has all our contacts, and I introduce you today, my colleagues from R&D and Innovation Department, that is a branch of the Software Development Department that is based in Padua. But as I said, we have branches also in Rome, Milan, Genoa, and Bologna. So it's a pleasure to introduce you my colleagues, Stefano Delli Ponti, Daniele Turato, and Gioele Perin from Innovation Department.
Okay. Good morning. I'm Stefano Delli Ponti. I'm the head of innovation in Siav, and I manage the R&D department. With me, Daniele Turato, the team leader of the R&D group, and Gioele Perin, which is the researcher who will give the actual talk today. Today we will. Okay, perhaps. Colpo di mouse, okay. Today we will present an approach to make search more flexible using text embeddings and extending our standard full text search engine. I will give. We are implementing just now this approach. So research as a practical, immediate target in our products. So it's an example of a research and the application directly in our products. I will give a very short overview of the company, and then let Daniele explain what we do in our R&D department. And the specificity of it in Siav in our company. Finally, Gioele will explain our approach from a technical point of view. Okay, Siav develops digital solutions and provides services to effectively manage content, information, and processes within an organization. We often say we often hear about digital transformation, and this is a good way to explain, to understand what we do. We help companies to work with documents, to organize, process information, and to collaborate in a paperless environment. Siav is a group, as Georgia said before. We have the main offices, the head offices. They are in Padua, Ruvano. We have offices in Milano, Roma, Bologna, Genoa. We have a subsidiary in Switzerland, a subsidiary in Romania, and Siav is making many corporate acquisitions these days, and to expand its business and its technological scope. Metric and credit service are our latest acquisitions or participations. Now we have more than 300 people working in Siav and thousands of customers. Our products, what we do, we develop what is called enterprise content management. It is a tool to process and archive documents, to using workflows, to assign tasks to people, and in general to collaborate among offices and teams in a company. Our main product is named Archiflow, and we are actively working on the next generation tool which will be called Syllogen. This is a portion of our customers. We focus on large companies, and both in the public sector and in the private sector. And then, before letting the floor to Daniele, I would like to say that Siav is a very intriguing and interesting place to work in. We have a large department. We are always looking for people, talented people to work in our technical departments, like development, QA, and research. And we are employing now about 100 people in these technical departments. I add that it's not so common to have a department specific, dedicated to research in a company, and to have such a good focus on research, even if with practical target in a company. So it's a good opportunity to work in Siav in this area. I'll let Daniele speak about the research areas that we work in.
So hi everyone. As Stefano was saying before, I'm the team leader of the research and development team. Okay. What does it mean, research and development in Siav? Okay. It means that our duties are to try to design and develop, let's say, develop prototypes, okay, of new solution to be proposed in the market. So this is the primary duty. The secondary duty is instead working in some projects, in particular addressing peculiar needs of this project where some particular skills or technologies are required that are usually not part of the, let's say, of what the development department usually works with. Okay, and this is where conventional techniques like phase. So, for example, you have to you can't deal with a problem like in a deterministic way, and for example, you have to use like a machine learning models and this kind of stuff that usually are not used by the development department. So we have to know many technologies that we see briefly in the next slide. And given that these technologies are fields, okay, quite big fields, okay, to have enough skills sometimes to work, okay, on these kind of things, we need help. We need help from you, actually, from the university. So we maintain active collaboration with the academic world, like the thesis, internships, okay, and sometimes also participating in partnership with the university to fund the projects, okay. In some software houses, R&D is something like a secondary duty of the development department. So it's like some part-time job, sometimes relegated to just a few hours a week. Okay, try to find new ideas and look for new technologies. Okay, instead in Siav we think that innovation is essential. So we need a dedicated team, we need a dedicated budget, and we need specialized professional figures, okay, that can study and acquire those skills necessary to deal with this kind of work. Okay. So to come out with innovative solution, you should look at many fields. The main ones that we are working on, you can see here in this slide, okay, and mainly they involve machine learning, okay, information retrieval, process mining, robotic process automation, and also something about blockchain. I will just briefly describe, okay, what does it mean using these technologies to come out with new solutions, okay, and innovation. For example, in particular in the field, we talk about the fact that Siav works in the document management field, okay. So using machine learning in the document management field, what does it mean? It means, for example, using, okay, NLP models. So, for example, you can think about a text classification model to automate some processes. So, as an example of document management process, you can think about the fact that in some companies in Italy, you have what is called posta elettronica certificata, so certified electronic mail. And so you have even big companies having one single mailbox, and there's actually people manually reading those emails and sorting them through too many different offices based on the content of these messages. Okay. For example, we can use machine learning, like a text classification model, to automate this kind of action. Okay, and so to optimize and to have a more efficient process. A couple of words also about process mining. So mainly these are the two main fields, let's say, and techniques that we use, okay, in our job. Okay, process mining is a set of techniques to understand and measure business processes. So what does it mean? Usually, to understand what's happening in a company, to understand if this company is working efficiently, usually you have to go there, ask questions, talk with people actually performing the work, okay, and try to come out with what's happening there. You have to figure out yourself, okay, what's happening there. Instead, using process mining, you can connect to information system supporting the different processes in the company. And you can so extract, okay, event log data describing actually those processes. And with these techniques, you can automatically build some graphical representation that can show you what's happening and how it's performing. So how the different processes are performing. Of course, we focus mainly in these techniques we focus mainly on document management process. So we use these techniques to provide optimal document management processes to our customers. And the third main field we deal with is information retrieval, of course, the reason we are here today. Okay. So we use it, of course, to provide effective search features in our products. And as an introduction to what Gioele will show you in a minute, you have to know that when we're talking about searching in our document, usually 90% of the time in Italian, in a wide variety of formats. So you usually have the main Microsoft Office or LibreOffice formats, okay, emails, PDF files, but also optical scans, okay, containing both structured and unstructured data. So you can, if you think about unstructured data, you can think about any document with textual content, with this descriptive textual content, like a document describing a project and so on. If you think about structured document, you can think about, for example, an invoice. Okay, so where the text usually are in boxes with a particular meaning. Don't think about structured data is not structured data is not always in a structured format. So it can be like a scan of an invoice. So in that case, the structured content is not easy to use. Okay. Just for a brief description of what we deal with. Okay. I give now the word to Gioele. Just I want to add last that given this third duty, okay, you are free to ask, okay, if you're interested, you are free to ask if you want to do some thesis or some other work with us, an internship or something. You are free to write me, okay, and we can even, I mean, if you're interested about some of the fields I have just presented, okay, and we can agree on some kind of work together. Okay. So.
Hello everyone, I am Gioele and I work as a research engineer for the research and development team in Siav. And I try to give you kind of a high-level overview of the process that goes into developing one of our projects which are required by our customer. In particular, here we will be talking about one specific requirement which was made by one of our customers, which consists in developing a system to improve the flexibility of a standard search engine. And here we have to understand what our customer meant by a standard search engine. And this is the standard implementation of a full text search that you can find in a system like Elasticsearch. So you will have the strict match of the words in your query with the words in the documents. And here we include also the ability to use stemming of the words and stop words removal, since they are very trivial to implement in a system. So to deal with this requirement, we have to take into account three major issues and three major questions that we have to find an answer to. And the first one clearly is how do we make such a project in the first place? And in particular, we have to make the system more flexible, but at the same time, our customer wants still to maintain an acceptable level of precision in the search result. So we want a system which will kind of just improve the results returned to the users. The second issue is quite a hard one to solve, and is how do we make such a solution fast enough for a production environment? And this will filter out a lot of the approaches that you might find in the literature, because once you start adding features to one of your projects, you will inevitably increase the computational cost and therefore making it slower. And there are some very strict requirements related to the performances and the hardware that we can dedicate to a specific feature. And finally, is how do we integrate this system in the existing product, which is based on Elasticsearch. And this requirement is the most difficult one, because it will limit us to exclude another big portion of solution that you might find in the literature. And we don't really have a say in changing the base system based on Elasticsearch, because other large departments of Siav have developed a lot of infrastructure which is based on this, and they would have to start from scratch if we were to require a change in the ground of the project. And we have also to understand that our project will just include a small feature in an already very large project which is used by our customer. So first we have to start by understanding what Elasticsearch is. And Elasticsearch is a distributed, free and open source search engine which is built on the Apache Lucene search library. And it allows us to store and retrieve documents with multiple searchable fields. This is a relevant property because we want to be able to store and search based on, for example, just the text of the document, but we want to be able to search also based on, for example, the user who produced the document, the date that the document was produced on, and by having multiple fields, it is very easy to implement this kind of retrieval system. So now we will go through a few of the main reasons why we and the other department chose to use Elasticsearch. And the first reason is that Elasticsearch is very fast and very solid when you have in instances when you are storing and indexing your documents. And this translates to the fact that the time that the user has to spend waiting for a document that he has just uploaded to be able to retrieve it with a standard text query is usually very low. And here we're talking about an order of magnitude of a few seconds. And also it is very fast when retrieving documents with the standard full text query. So the ones we have talked about earlier. And here we're talking about milliseconds. So for the feature that we are going to implement, we will have to get performances which are still similar to the one that you can achieve with the standard features provided in Elasticsearch. The second big reason why choosing Elasticsearch is that it is a distributed system in nature. And the reason why we care about having a distributed system is for two main reasons. The first one is that by using multiple nodes, you can store multiple copies of your documents across several nodes. And this is very relevant for us because by storing multiple copies of a document, we can make them redundant. And if one of the nodes were to fail because the node broke, we are not allowed to just lose the documents and tell our customer that we cannot do anything to retrieve them. But if we have copies stored in other nodes, we can just recover the data that we lost in the node that went down. The second reason is that with distributed system, we are allowed to scale horizontally. And this is a strict requirement because when you are dealing with a few 100,000 documents, you don't really need to scale to multiple nodes. But in our instance, for example, we are dealing with about 30 million documents to be able to store and search among. So when you have this amount of data, you will just not be able to have a single big enough computer to store all of the documents and be able to retrieve them in a decent amount of time. So the only solution here is to distribute the load across multiple computers. And if the amount of documents were to increase, you will just add another nodes and your system will still be stable and able to deal with your requirements. The third reason, which is often overlooked, is that the fact that Elasticsearch is an industry standard, and it is an industry standard because it's used by a lot of people, including several large companies such as Amazon, Facebook, GitHub, and Wikipedia. Although being an industry standard is not a feature of the system itself, it's something that we are searching for because by having a system which is widely used and maintained by a community, for us it is kind of a warranty that if we were to build a system on top of it, we will not have to throw away all of our work just because in a couple of years the system, the base of our work was thrown away for something new. And having something which is very solid, and it's solid because it's widely used, gives us the warranty that our work will be relevant for at least a few years. And if there were some major issues, they will be solved by the community or the maintainer of the project. Finally, and this is the last slide regarding Elasticsearch, is the most obvious reason, and it's because the main features that we have to use are already implemented, and they are implemented in a very solid way, and we know they work without major issues. And the two main features are full text, very fast full text search using the M25 scoring, and these also includes the ability to do some standard improvements such as stopwatch removal, as we said, and stemming, and a very fast filtering of the results, which will determine the documents that a user will be able to see when making a certain query. Now that we know why we choose to use Elasticsearch, we have to be able to better understand the requirement of our customer, which was just make search but flexible. And by talking with them and understanding what their actual requirement was, there were two main points that we have to take into account. The first one is that you might be searching for a certain document and you might not know exactly what to search for. So a document may be relevant to your query and therefore to the user, even if the document and the query have very few words in common, but there are some synonyms, for example, inside the document. So the first requirement is kind to be able to understand the concept of the words in the query instead of just a strict match. The second reason is that two documents which are sharing the same amount of words and therefore would likely have a very similar score when scoring with the standard system might not be equally relevant. And this is not obvious, but as an example, when you're searching for Albuquerque, which is a city, and you're searching for it in Wikipedia, for example, you might get these two results. And on the results on the left, as you can see, there is a short paragraph which is matching the word that you search for only once. But as you can see with the green words, the paragraph is actually about the city. So when you're searching for Albuquerque, it's likely that you're searching for the paragraph on the left. While the paragraph on the right is still having exactly one match with the query, so it would likely get a very similar result, similar score when you're searching for that word, but it's just mentioning it, and the context of the paragraph is something completely different. So we can suppose that you are not being able to search for it. And the meaning of this requirement, therefore, is that we have to take into account also the context of the query and the context of your documents, and not just the strict match of the words. So now we understand kind of the requirement of our customer. And the good news here is that there is kind of a technique which has already been developed to deal with all of these issues, and it's called text embedding. It's a technique that has been developed by the natural language processing community. And the intuition behind this is that it allows you to encode sentences or singular words into dense vectors with dense numerical vectors, usually with a number of dimension that goes between 100 and 1,000. And as you can see from the image, these dense numerical vectors are able to kind of grasp the semantic context, semantic meaning of the context of a sentence, and it will be very similar for words or sentences which are sharing the same meaning. So this seems like a good direction to follow for our system. And the other very good news about this approach is that text and word embeddings are usually trained using machine learning algorithms, clearly, but they are trained in an unsupervised manner. And this is very relevant because having to use supervised machine learning algorithm for us require a lot of human labor and therefore a lot of money to produce the data sets that are usually kind of a blocking issue. Instead, by having just an unsupervised machine learning algorithm, we can take some publicly available text, like the corpus of Wikipedia is widely used to train the system, or if our customer were willing or allowed to give us their documents, we could train our word embeddings directly on the documents of our customer to get a solution tailored for their domain. And we know then that we have this dense vector that are able to represent the concept of a sentence or of the words. And the way we can use them for a query is by following this pipeline. The first step is clearly we have to train our embedding model on either some publicly available text or the text given by our customer, or another very common option is to just download a pre-trained word embedding model. And this is a common option because training them can often be quite expensive to do for the computational cost. The second step consists in converting each of the documents that you are going to search in into their embedding representation using this given embedding model. And the same thing we will do with your query vector. Then, when you are retrieving your documents, you just assign to each one of the documents in your index a score which is based on the distance between the query embedding and document embedding. Here, by distance, we mean some sort of similarity measure, and in our particular case, it's the cosine similarity, but it usually depends on the way the embedding model has been trained. And finally, you just return the document with the best score to the user. Now, the system, it looks like kind of solves the problem of having a flexible search engine, since we know that the embeddings will be similar for documents which share the same context of the query. And this is actually, in fact, the good part of an embedding search system, since, as we said, they are effective in grasping the semantic content, and synonyms are represented kind of automatically, since similar, they are kind of included in the context of the system. So we could conclude that an embedding search is more flexible compared to the standard approach based on the standard BM25 scoring with the strict match of the words. However, the project unfortunately does not end here, because there are some relevant drawbacks. And the first drawback is that we get a very flexible system, but we also get a much less discriminated system. And we care about a system which is able to actually discriminate between the documents, because when you are searching for something, if you don't know what you're searching for, you would likely be satisfied with just embedding search. But if you know what you're searching for, and you just want documents which have match with your query words and the same context with your query, you will likely not get this result with just an embedding search, because it's not taking into account the exact matches of the words. So this is the first issue to take into account. The second very relevant issue, and the one which is blocking for us, is that terms which are not seen when training your embedding models will just be ignored, or will be treated as noise in the worst case. And this is a very relevant issue, because in particular in a business scenario, you are often searching for things such as names, codes, and specific terms for the field. Like if you have a very technical domain, you might not get all of the specific terms that a user might be searching for. So ignoring them would likely result in very bad search results for the users. And finally, long documents are very difficult to represent with a single vector. You will likely not notice this issue when searching among documents which are a couple of paragraphs long. But when you have documents like the business scenario, as we said, which have several pages of text, then having a simple vector representation for dense vector representation for these documents will likely result in a very diluted vector, since many different contexts might appear in the same document, and you will just get the average context, which doesn't really maintain much of the meaning of your document. The issues related to the quality of the results returned as there. However, there are some other blocking issues which are related to strictly the efficiency of this approach. And you might have understood it from when I explained it, but when you determine the score and therefore retrieve the documents with the highest score, in the instance you're making a query, you will need to compare your query vector to each of the document vector. And as always, this is not much of an issue when you're searching among a few 100,000 documents, because it will take a couple of hundred milliseconds to do. But when you're searching among 30 million documents, this will take several seconds to do from the perspective of your CPU load. And this is not even the worst part, because if you have enough dense vectors to store, they might not be able to fit into your main memory. And this will therefore result in several disk loads, which are extremely slow and will take your response time from a few seconds to likely a few tens of seconds. And this is just unacceptable, because when you're making the query, you expect to get a result in an amount of time which is barely, which you are barely able to see. And waiting for 20 seconds will just result in a system that the user do not use because it's very slow. And besides, there's the issue that you will be saturating the resources of your cluster for all of the other features which are expected to be fast. So to sum up, to get kind of a sum up of the scenario where you could use embedding search, it will likely have very good performances in moderately sized indexes, like as we said, a few 100,000 documents up to at most 1 million, depending on your computer. Relatively short document, and here, however, we're still talking about a couple of paragraphs, which might be considered a lot of text in other scenarios, and the absence of specific terms such as names, codes, etc. So if you're searching among the paragraphs of a Wikipedia page, this might be a very good solution. However, in our system, where this scenario is not met, a search engine which is based only on embedding search is likely not the most effective solution. And this is both due to the results returned and the performances. So to deal with these issues, we have to propose a new solution. And the solution that we propose to deal with the issues of the results which are returned to the user is to propose a hybrid approach. So we saw that there is a system to kind of get the context of your query and your document. So we will use that system to get a score related to just the context of the document. But we will still use the standard the M25 scoring system, which Elasticsearch is using, and which is strictly based on the match of the words. What we do then with these two scores is we normalize them to be able to compare them apples to apples, as you say, and then we return to the user only the documents with the highest overall score. Now, the results of using this approach is that, also always going back to what our customer required, documents which are semantically similar or sharing the same context with your query will have a high embedding score, and documents which are sharing a lot of terms will have the high M25 score. So if you get a high score on both of them, you will get these results on top. However, when you have some unseen terms which are just not taken into account from your embedding model, you will still get results which are taking into account this unseen term, because you will have a not very high embedding score, but a very high M25 score. So they will likely appear in your search results. And finally, for the issue of documents sharing little term with your query, but which are semantically similar, like in the case of the query and query that we've seen before, you will have the opposite situation where your M25 score is not very high, but the score related to the embedding search is instead very high, and therefore will bump your results to the first places. And as we've seen, this approach is able to kind of take into account all of the issues related to what our customer required. However, as you might see, this system is not improving the performances at all. Instead, it's decreasing them, because we're also adding another query to do in parallel. And so we have to find a way to improve the efficiency. And the first step that we took was to go and look into the system which Elasticsearch is implementing. And they are implementing a system to index, and here index is not the proper word for dense vector, but it's a system that is allowing you fast retrieval when you're searching with an embedding model. However, it has two main drawbacks. The first is that it doesn't allow for the use of filters on your search results. And this is a mandatory feature in our system, and we will see in a couple of minutes why we need it. The second drawback for the system that they implemented is that the feature is still in technical preview. And we talked earlier that we want a system which is an industry standard because it gives us the warranty that when we build something on top of it, we will not have to do it again from scratch if the system were to fail. And here, the Elasticsearch team is telling us that this feature exists, but in a couple of months, they might change it completely or remove it altogether. And therefore, it's very risky for us to go and implement an entire system or an entire feature for a customer based on a feature which might disappear in a couple of versions. So here arises the need for us to implement an alternative solution. And that's what we did. First, however, before going and looking into our solution, we have to understand why filters are a mandatory solution for our customers. And the reason is that in an organization, different users might have access to different documents. And for example, an office might be able to see only the document it's working with, while not having access to the documents managed by a different office and vice versa. This is an issue this is a requirement which is both related to some company policy, for example, because they don't want the various team to be able to see what the other is doing, but there are also some very strict laws related to the privacy of their own customers, where they have only some offices will be allowed to see certain documents, and if they were to be leaked to other offices, then there would be some serious issues. So this results in a feature that we have to implement, and if it weren't available, we wouldn't be able to provide an effective system. The way these filters are implemented in Elasticsearch is as Boolean conditions. So we said earlier that Elasticsearch allows you to store your documents using different fields. Let's take the example where you're storing the text extracted from the document in a field which is called text, and the office that produced or is using a certain document in the field office. So when you have a user coming from Office 1, which is searching for a certain query, your query will not just be related to the match of the words in the query of the users and the words in the documents, but there will be also a Boolean condition where you have to get the match for the query and the match for the term Office 1 in the field office. If either one of these conditions were not to be met, then the document will not be returned to the user. And in this way, you are enforcing the ability to exclude some users from being able to see certain documents. Now we can go and look into the way that a way where we can improve the performances of the system. And when you are searching in the literature for approaches to improve the response time in the k-nearest neighbor approach, which is basically the search with dense vectors to search the most similar other dense vectors in a certain corpus. The most proposed approach is an approach which allows you to approximate the results returned. And although there are several different approaches in these subfields, they all share the same intuition, which is that you will compute the exact similarity between two dense vectors, only when you can estimate that the embeddings are similar. And this estimate will usually be achieved by using certain specific data structures that allows you to get it in a very fast way. And the result of doing so is that you therefore reduce the number of exact computation that your system has to execute. And in this way, you are both reducing the computational load on the CPU and also the amount of documents that you have to load into the main memory at each query. The way that Elasticsearch is indexing the document is actually by using one of these approximate algorithm, and they are using an algorithm which is called HSNW, which, by the way, I believe is the state of the art for this kind of field. And however, it doesn't implement the ability to filter out such results, and this is due to some difficulties in implementation, and they don't really know when they'll be able to include these features, so we are not able to use their solution. Instead, we chose to go for a different route, and we chose to use an algorithm which is called Locality Specification. The intuition behind this algorithm, and we have to understand that there are several different sub-algorithms related to locality sensitive hashing. They all share the intuition that you will hash similar input items, which in our case are the embedding vectors for the document and the embedding vector for the query, into the same bucket or hash code, and this will be done with high probability. As you can see in the image, all the items in blue are shared into bucket 4, all the items in green are shared into bucket 3. And the way we are using this algorithm is that we compute the bucket where our query ends up in, and we compute the exact similarity only on the documents that are in the same bucket of our query. Now, you might see from the image that some items in blue are very close by to some items in green, but are not sharing the bucket. And this is an issue because you wouldn't be able to retrieve the documents, the close by document in green. So to maximize the probability of retrieving all of the similar documents, what you do is you compute several different hashes, which are several different versions of these buckets, and you do that with different functions, so that they are all shuffled around. And in our approach, we will search, we do the exact similarity computation among all the items that are sharing at least one hash or one bucket with our query embedding. So the way this translates to the pipeline of the query for Elasticsearch is you maintain the first two steps, which are to train the embedding model and convert the document to its embedding vector representation and the query to its vector representation. But here is the difference, where because you have to also compute the hashes for the embedding vector that you are indexing. And the way you use these hashes in Elasticsearch is quite simple, because you just treat each hash as a different term, and you store these different terms as a text field, which is indexed and is therefore has a very efficient way of retrieving documents with a certain hash. So at query time, you compute also the hash for your query, and before doing the exact computation between the vector, you go and retrieve all of the documents having at least one hash in common with the query. And this is done in a very fast way by doing a simple full text search in Elasticsearch. And you go and compute the query, the similarity between your query embedding and document embedding only on the first n documents having the most amount of hashes in common. Here, the amount of hashes in common works as the estimate of similarity that we talked about earlier. So this is a good approach, because while earlier the computational cost of our query was linear with the amount of documents stored in our index, because we would have to compute the similarity between our query embedding and each document embedding. Here, the cost becomes constant, because we compute the exact similarity only on n documents, which are the top n documents returned by the full text query on the hash field. And the other part, which will scale with the amount of documents stored in Elasticsearch, is the full text query, which is luckily very efficiently implemented by Elasticsearch, so it's not that big of an issue. And finally, you compute the exact similarity and you return the documents with the valid score. The pipeline we showed here is related only to the embedding search, and that's because including it in the overall hybrid search would be quite difficult to represent. So here we can see that the overall structure of the query will subdivide the query in two main blocks. The first is what we call the top query. And in the top query, you do all of the operations related to the filters for your specific user, the full text query on the document text, which is used for the hybrid approach, and the query on the hashes. All of these operations, as you can see, are the kind of operations which are very efficiently implemented by Elasticsearch, so they will not take a large amount of time. And the role of this top query is to return only the documents which can be seen by the user, and only the documents with the highest estimated overall score to then be fed to the rescorer, which will compute the exact score, again, only on the first n documents returned by the top query. And as we will see later on in the performances evaluation, this approach allows us to significantly reduce the cost of our queries. First, however, we will take a look at the quality, we could say, of the results returned by our ideal approach. And the way we chose to show these different results is also related to the way that our customer might be able to better grasp the differences, because when you propose them a solutions based on some common text collection, for example, you will tell them, okay, we increase the recall, the precision, and everything else, but you are not talking with some very technical people, and they will likely not understand what you're talking about. So the best way to show them that our system is working and is satisfying the requirement is by actually showing the differences between the old system that they were using. So here we go to 3 different queries that we executed on text corpus, and we show the different results returned by the different solutions. And in particular, we will compare the standard results that are returned by a query done by standard solution implemented by Elasticsearch, including stemming and stop word removal, and our proposed solution, which is the hybrid search. Here, the documents are in Italian because we had to use Italian documents since our customer is working on the Italian domain. And the first query is alluvioni non anda Germania. Here, the user is likely searching for some news or some information about very bad weather in these 2 countries. And with the standard approach, you can see that the last results are all matching both the words Olanda and Germania, but are not matching anything related to the weather. So they are all related to some kind of agreement between these 2 countries, and therefore these results are not relevant at all from the perspective of a user which is searching for alluvioni. Instead, in our proposed solution, not all of the results are matching multiple words. Most of them are matching just one, but they are all related to the concept of weather and bad weather. As you can see, there are some related words to alluvioni, like well tempo in most of them, maltempo, inondazioni, acqua piena, etc. So these results shows that here we are able to take into account the context of the document of both our query and the documents that we are returning. The second example that we chose to use is a particular query, which is limitazione sul fumo. Here we are searching, we are likely searching about some new legislation about smoke or something like that. And the particular thing about this query is that the 2 main keywords, which are limitazioni and fumo, never appear together in a document. So at most, you will be able to have a single match. And it just so happens that the word limitazioni, on average, has a higher BM25 score associated to it. So what you get with the standard approach is that all of the results are matching the word limitazioni, but none of them is about the concept of smoke, cigarettes, etc. So pretty much no result at all is relevant for the perspective of a user searching for limitations on smoke. In our proposed solution, instead, we are never matching the word limitazioni, we are only matching the word fumo, but in blue you can see there are a lot of related words to the concept of limitazioni, such as norme, stop, and limiti. And limiti is a particularly fun one because it's just, you might think that it's included by the stemming approach. Instead, it's just a different word from the perspective of stemming. So it's an obvious synonym, but which is not taken into account by the standard approach. Instead, in this example, we can show that our system is able to take into account also synonyms and very related words to the words of the query. And this is the instance where you are not exactly sure about which words to search for because you don't have a particular article in your mind. And the last comparative results is a bit more of the same because we are searching for bancarotta della Perin, and here we're searching about some results where the user might be searching for some results related to the bank bearings and some of the revenues that we just received. And in our standard results, some of them are relevant because they're matching the word bancarotta or bearings. But as you can see, in for example, the last two results, we are talking about bankruptcy of the city of Washington or a film. And these results are just not relevant at all. In our proposed solution, instead, we are not matching the word bancarotta, but we are also matching the word bearings, which is a specific word because it's the context or because it's a proper name, which is likely not represented by the embedding model. But we're matching it, and the high matching of the context given by the presence of words like bank, truffa, inchiesta, crollo, etc. And these again goes to show the fact that we are able to take into account the specific terms while at the same time getting a more general grasp on the context of the documents that we are returning. Now that we've seen the quality, we could say, of the results returned to the user, we will take a look at the efficiency of the system that we implemented with our approximate solution, which is in blue as opposed to the exact solution. The way we evaluated the performances and the response time is by simulating multiple users, which are all searching at the same time among 1 billion different documents. And as you can see, as you increase the number of users, the amount of time spent when doing the exact query, which is comparing each document to each document embedding to your query embedding, goes to increase because you are saturating your CPU. So you increase the amount of time that the user has to wait. While with our system, the CPU is pretty much never saturated. And as you can see, while increasing the number of users, the amount of time they have to wait is quite low. However, when seeing these two results compared, you might think that the results are not that impressive. And I would agree because the difference is not that perceivable. However, we have to take into account that when searching among 1 billion different documents in the test machine, the system was able to maintain all of the index into the main memory without saturating it. So here we're taking into account just the difference in the cost from the perspective of our CPU and not from the perspective of the disk usage. Instead, when we increase the amount of documents which are stored in our system and we bump it to 3 million documents, the system is not able to maintain them into the main memory anymore. And what happens is that when you have to do a query, you have to load the specific vectors to the main memory and then compute the exact similarity. This operation is still expensive, but not very expensive when loading a little amount of documents into the main memory. When you have to load 3 million documents into the main memory, you see that with 4 concurrent users searching among the documents, they have to wait on average 25 seconds to get a result. And this is clearly not an acceptable solution. So it goes to show that using an approximate search approach is kind of the right way to improve the performances, although it still requires some fine-tuning. To wrap up what we just explained and to get the clear comparison between the standard embedding search, we can show 3 points. The first is the fact that by approximating the output of our query, we are reducing the computation needed and therefore we are improving its performances. Also, by using the hybrid approach, we are taking into account the specific terms which were otherwise ignored by the embedding model. And at the same time, when talking about long documents, the full text search is usually quite effective because there are a lot of words and therefore you increase the probability of matching at least one of them. Here we are not decreasing the performances of the standard search, we are maintaining them and sometimes increasing them, while using the standard embedding approach was significantly decreasing them because it wasn't able to get a precise representation of the context of such large documents. Regarding the state of our work, there is still a lot to do, and in particular, we have to fine-tune the efficiency of our query to satisfy the required performances, because when searching among 3 million documents, we are fine, but when searching among 30 million documents, there are still some inefficiencies to take into account, which require us to kind of determine where they're coming from. And finally, we have to define an optimal embedding model based on the documents used by our customer. And this is quite a difficult issue to take into account, because when you go and search into the literature, the way embedding models are studied right now is by developing them for text, which is something like what you would find in Wikipedia, for example. So some very unstructured text with a discursive approach. Instead, our customer is searching among some kind of this text, but also among a lot of tables, a lot of very structured text. And what we saw is that by using the embedding models proposed in literature, which are treated as the state of the art and are usually based on, for example, transformers or LSTM, we are getting very bad results on documents which are something like tables or very structured. Instead, they work very well on standard text collections such as clef, etc., which are usually taken from the news and therefore are very discursive and are working in the specific domain for which these embedding models are developed. And with this, we kind of concluded our presentation. So I would like to thank you for your attention. And if anyone has some questions, we are happy to answer them and give you a more precise perspective of the project.
So any questions, curiosities, comments?
Yeah, I had a question on the hashing technique that you used. If I understood it well, it was like you are clustering the documents into some hashing buckets.
Yes.
And then you are performing the search into the hashes. So you are searching for hashes now, and not for specific terms.
Okay. The locality sensitive action is used for, we are using an hybrid approach where we do a search on the embeddings of the document and a search with the standard approach based on the input file. And we treat them as two parallel and kind of modular pieces of a query. The locality sensitive action is part of the embedding model. So when we search for something, we do what you would call a multi-match query, where you have to match both the terms for the specific query, and this is done on the text field, and the hashes for the embedding model, which are stored in a different field in Elasticsearch. So for each document, you will have multiple fields, like the text field with the specific text, the office, the author, etc. And by using locality sensitive action, we add another field, which is again a text field, where we store the various hashes. And we use one of these fields because they are very efficient to search. So, again, the result of that specific query was to represent an estimate of the similarity between the query embedding and document embedding. Because if you have one hash in common, it will likely be similar, but if you have 30 hashes in common, it will likely be very similar. So that works as the estimate.
Okay, thank you. Yeah, my doubt is like, because we mainly the hashes like one-way functions. So it's like if you change even one character on the query, the hashes
No, exactly.
I guess this is an issue of how these hashes are used.
Yeah, this is kind of yeah, it's difficult to imagine to call this function an hashing function because you are expected to have hashing function which reduce collisions. Instead, in our case, we are trying to develop a hashing function where we can control the amount of collision, and we can focus the conditions to appear only when two inputs to the given hash are very similar. What we do in this particular case is a hyperplane projection. So you divide the space where your word embeddings are laying into multiple parts, and the hash and each part that you divide the space represents a different hash. And by doing so, you have that all of the embeddings appearing in the same part where you divided the space are likely similar because they appear in the same part, and therefore you search only on the documents in that part.
It's random projection, right?
Sí.
The name of the hashing thing.
Sí.
Okay, you can search for a random projection hashing.
Okay,
Or
okay.
LSH algorithm.
Oh,
And
If you're curious about
yeah.
yeah, the advantage of that technique is that it's also very trivial to implement in Python, for example. So there are a lot of techniques that you can implement, but not all of them are already implemented on GitHub, for example, from the authors. So it's very difficult to reproduce the results. A very simple one that you can play with is random projection, as Daniele said.
Questions? So, sorry, I mean, so you are doing a field-based retrieval somehow because you said field-based because you have different fields. One field is for hashes, one field is for text.
Yeah, exactly.
And then you do separate. I mean, you use Elasticsearch to match these fields, and then you do that.
Exactly. Yes, Elasticsearch allows you to do several parallel queries, and then you combine the score of the several parallel queries, and you can choose how to combine them by using some internal scripts of Elasticsearch that you can write in a specific language. And we do exactly that. So we do one query for the hash, one query for the text, one query to filter out the results that the user cannot see, and we then combine all of the score for the various queries.
And then the scores are combined by Elasticsearch, so you use a PM25 with fields and weigh everything in a single output.
No, that's different. It's not a feed that we have 25. They have a different object they use to do that.
So it's not.
I mean, you've seen and then in Elasticsearch, it's somewhat similar to rank fusion, but not exactly because that is done yet with another component.
So a particular thing you have to take into account is that although Elasticsearch is based on Lucene, it works as a wrapper to make things simpler for the developer and the user. So not everything of what you can do in Lucene, you can do in Elasticsearch.
Other questions?
SPA models works fully for your data. So kind of embedded models are using.
We are still evaluating some of what model to use. Right now, our customer hasn't given us some documents to test it on because they have very strict laws they have to follow for privacy. So they have to first deal with the laws and then give us the document. So what we did right now is to use other test collections, which are still based on rules, for example. And here we are using embedding models which are based on that. What we expect to do when we are doing this kind of search in our document, in our customer documents, is that we use some kind of simpler technique which is able to kind of get what kind of words appear together, which is the relevant thing when we're talking about tables, because like, the word IVA and the word conto usually appear together when we're talking about a symptom. And if you're searching for conto, you'd like to get documents which are high context, all of these similar words that appear together. but we have to see when our customer will give us these documents. It's in fact it's still a work in progress part of the project.
Everything that
I have more of curiosity that's not directly related to the presentation, but like I saw that like, you have a lot of different customers that like tons of different domains. Have you considered start maybe already doing some knowledge extraction on data so that you have so that you can build more like entity-oriented type of search engines, or doing something more like question answering kind of customer that you have? Like I don't know if like getting knowledge in a more structured way out of your free text documents that you have, or even semi-structured, whatever, and then store that kind of thing to be used later on for increasing or improving the way you're performing searches, because you have a ton of different like ways to perform retrieval, so you're caching and you have EM25 or embeddings. What happens? What if you like insert like a new phrase, at least like a new kind of field that you can use that you make mainly on relevant entities that your customer might want to have?
We were thinking about doing some kind of intelligent query expansion, where you get the query and some kind of system based on some kind of technique is able to get some words which might be relevant with your query, which is kind of similar to what Google does. When you search for something, it tells you maybe you were searching also for this. However, it's still quite difficult to do because it's hard to understand which words will actually improve on the results of the query. And that's difficult because when you have embeddings, you have something which is which has a very continuous representation of the similarity. While if you had one specific keyword, you will bump the results of the documents matching that specific keyword, but it's not sure that you will improve the results of the search.
Yeah, no, I completely understand about this. So like, if you have customers that have specific type of entities, like in the legal domain, you might have like patents or things that you already know that are relevant and they're looking for exactly those kind of things. You can get like graphs or other kind of structures that work in parallel to the unstructured way you retrieve things and then combine them at the end with like depending on the way that you want to give them. But like it is more like an entity search that works all together with the textual one, but on a different underlying data that you store.
No, so far no. Okay, so this is interesting because I mean we thought in the past about something specialized for some particular things like the legal one you just told, but in this particular project, I mean we basically I mean Gioele is talking about a particular customer, but we wanted to provide something that we could have used to most of our customers. Okay? And so in this particular project, we didn't focus on a particular field, but that's interesting. Okay, and we can talk about this. Okay. Thanks.
Any other questions? Okay, so thank you very much for and I think it's all for today.